You're watching this because someone said the word wormhole, and something in you sat up straighter. Maybe you've seen the headlines. Scientists may have found a real wormhole. And some part of you wants that to be true so badly, it almost doesn't matter if it is. Here's the strange part. In January of 2026, a team of physicists actually did publish something, not science fiction, a real paper in a real journal. And it touched the exact bridge Einstein himself once sketched out back in 1935 with a young researcher named Nathan Rosen. But before you get excited, I need you to sit with a harder question first. What if the thing they found isn't a tunnel at all? What if it's something stranger? Something that was never about traveling through space, but about slipping through time. Stay with me, because by the end of this, you're going to understand why physicists have spent 90 years chasing a shortcut through the universe, and why the answer they just found might be more unsettling than the shortcut itself. Let's go back to 1935, because to understand what just happened, you have to understand what Einstein was actually looking at. He wasn't trying to build a shortcut through the universe. He wasn't dreaming, not in the way we dream now, of doorways and distant galaxies. He was trying to solve a problem that had nothing to do with travel at all. He was trying to understand what a particle actually is. Einstein and his young collaborator, Nathan Rosen, were staring at the equations of general relativity, the same equations that describe how mass bends space, how a star curves the fabric around it enough to hold a planet in orbit. And somewhere inside that math, they noticed something strange, a kind of bridge. Two regions of space-time, connected, folded onto each other like the ends of a piece of paper brought close together. They called it a bridge. Today we call it the Einstein-Rosen bridge. And later, another physicist gave it the name that stuck in all of our imaginations: wormhole. Coined by John Wheeler in 1957, after the tunnels a worm leaves behind in a piece of fruit. Not exactly poetic, but strangely accurate. Here's the thing nobody tells you in the movies. That bridge Einstein found, it isn't stable. It isn't something you could walk through. The math shows it collapsing the instant it forms, faster than light itself could cross it. It opens and closes in a single violent breath, and anything trying to pass through would be crushed before it ever reached the other side. So for almost a century, that's where the wormhole lived. Not in our sky, not in our reach, just in the math. A beautiful, technically real, completely unusable idea. And maybe that would have been the end of it. A footnote in physics. A curiosity mentioned in classrooms, then forgotten. Except scientists kept circling back to it, because there was always this quiet, nagging feeling that the bridge meant something more than a mathematical accident. In 2013, a theoretical physicist named Juan Maldacena noticed something that made the whole field pause. He was studying entanglement, that strange quantum connection where two particles seem to know what's happening to each other, no matter how far apart they are. Einstein famously distrusted it. He called it spooky action at a distance. It bothered him for the rest of his life. But Maldacena found something Einstein never saw. He found that entanglement and wormholes might be the same thing, described in two different languages. He put it into an equation almost too simple for what it implied. ER equals EPR. The bridge equals the spookiness. Think about what that actually means for a second. It means the strange thread connecting two particles across a galaxy and the exotic bridge folding space onto itself. They might not be two separate mysteries. They might be one mystery wearing two different masks. That idea changed everything, because suddenly, wormholes weren't just a leftover curiosity from 1935. They were a doorway into something physicists actually care about more than travel, a hint at how quantum mechanics and gravity might finally speak the same language, something scientists have been chasing and failing to find for over 100 years. And that brings us to now, to January 2026, to the paper that made headlines nobody quite knew how to write correctly. A team of researchers went back to that original Einstein-Rosen bridge, the one from 1935, the one that collapses in an instant, and asked a question nobody had asked quite the same way before. What if we stop trying to force it to be a tunnel through space? What if instead it's a tunnel through something else entirely? I want you to sit with that question for a moment, the way I did the first time I read it. Because if they're right, if that bridge was never about connecting two places, then everything you've ever pictured about wormholes, every doorway, every shortcut across the galaxy, every science fiction ship falling into a spinning tunnel of light, none of that was ever the real story. The real story might be about time. Not the kind you can travel through, the kind that begins. And that's where this gets strange enough that even the physicists writing about it chose their words very, very carefully. So here's what the 2026 paper actually found, once you strip away the headlines and get to the real physics underneath. Remember that collapsing bridge from 1935? The one that opens and closes too fast for anything to survive the crossing? The researchers looked at it again, but this time they weren't asking whether something could pass through it in space. They were asking what it looked like from the inside in terms of time, and what they found was two separate versions of time, folded back against each other. Two arrows pointing in opposite directions, meeting at a single point. Not a hallway, a hinge. I know that sounds abstract, so let me try to give you something to hold on to. Picture two rivers flowing toward each other, not joining into one wider river the way rivers usually do. Instead, at the exact place where they meet, both rivers turn around. Time for one side keeps flowing forward. Time for the other side is somehow flowing backward into that same point, not two places connected by a tunnel. Two moments hinged together like the spine of a book. That's the shift. That's why the physicists writing about this were careful with their words. Because if that's what the Einstein-Rosen bridge really is, it was never a shortcut anyone could walk through, even in principle. It was a seam, a place where two different flows of time touch briefly before pulling apart again. And I think that's the part that gets under your skin if you let it. We wanted a door. What we might have actually found is closer to an echo, the universe folding a moment of its own beginning back onto itself, for less time than it takes you to blink. But I want to be fair to the excitement too, because it isn't only this one paper carrying the story. There's a reason wormholes keep showing up in serious physics conversations, not just science fiction ones. And some of it is genuinely strange enough that even skeptical scientists lean in. Take Sagittarius A*, the supermassive object sitting at the center of our galaxy. For decades, we've called it a black hole, and most of the evidence still points that way. But a small number of physicists have floated a different, more unsettling idea. What if some of what we're seeing there isn't a black hole at all, but the mouth of something else? A structure that swallows light the same way a black hole does, but doesn't end the way a black hole ends. One that connects instead of erasing. There's no confirmation of that. I want to be honest with you about where the evidence actually stands. It's a minority position, tested against a mountain of data that mostly agrees with the ordinary black hole picture. But new instruments, built specifically to study the shadow around Sagittarius A* in finer detail, are slowly closing the gap between speculation and certainty. We may know within our lifetimes which story is true. And then there's the quantum computers. In 2022, a team working with Google's quantum processor did something that sounds almost like a magic trick. They didn't create a wormhole in the sky. They created something that behaved like one, mathematically, inside a chip small enough to hold in your hand. They encoded a tiny quantum system, sent information in through one side, and watched it emerge from the other, following the exact signature Maldacena's equations predicted a wormhole should produce. It wasn't a hole in space. Nobody climbed inside a machine and stepped out somewhere else. But it was real, in the sense that the mathematics of a wormhole and the behavior of that system were, for a moment, indistinguishable. A hologram of the idea running on hardware. Some physicists find that thrilling. Others find it almost cruel. Proof that we can simulate the shape of the dream without ever getting close to the thing itself. And now there's a third thread. A physicist named Ahmed Salih has proposed something even more provocative, a way to build a version of this using nothing but existing quantum technology, no exotic materials, no science fiction hardware. He calls the process counterportation. The idea is to send a quantum-encoded object through an entangled channel in a way that behaves, in every measurable sense, like passing through a wormhole. Not proven yet, barely tested, but serious enough that it was published in a real physics journal, not a fringe one. 3 separate threads. A bridge that might be a wrinkle in time instead of a tunnel through space. A galactic center that might not be what we assumed. A quantum experiment that already mimics the mathematics of a wormhole, sitting on a lab bench. None of them, on their own, gives us a door. But put them next to each other, and you start to feel something physicists rarely say out loud. That we might be circling closer to an answer than we've ever been before. Not because we found the wormhole, but because we're finally asking the right question about what it actually is. I want to slow down for a second, because there's a question sitting underneath all of this that we haven't touched yet. Why do we want this so badly? Not the physics, the wanting. Because if you strip away the equations, wormholes were never really about faster than light travel, not at their core. They were about distance, about the ache of it. Every civilization that ever looked up at a night sky full of stars it could never reach has quietly wished for a shortcut, a way to fold the unbearable gap between here and there into something small enough to step across. That's not a scientific impulse. That's a human one. And I think it's worth naming, because it explains why this story keeps resurfacing every few years, wearing a new headline, even when the physics hasn't fundamentally changed. So let's talk about the actual obstacle. The thing standing between a wormhole on a chalkboard and a wormhole you could walk through. It's called exotic matter, and the name undersells how strange the requirement really is. For a wormhole to stay open, for it to not collapse in that violent instant we talked about, you need something with negative energy density, not just low energy. Negative. A kind of matter that, instead of attracting everything around it the way gravity normally does, pushes back, holds the tunnel's throat open against its own desire to seal shut. Here's the problem. As far as we know, that kind of matter doesn't exist in any usable quantity. We found tiny, fleeting hints of negative energy in very specific quantum experiments. A phenomenon called the Casimir effect, where 2 mirrors placed impossibly close together seem to squeeze a small, negative energy gap between them. It's real, it's measured, it's also almost nothing. Nowhere close to the scale you'd need to prop open a hole large enough for information, let alone a person, to pass through. So for decades, this is where the conversation usually died. Wormholes, sure, in the math, but exotic matter in the amounts required. Probably never. And then Maldacena's insight cracked the door open again, because entanglement doesn't need exotic matter in the traditional sense. It provides something that behaves like the negative energy a wormhole needs, using nothing stranger than quantum correlations we already know exist. That's why the 2022 quantum computer experiment mattered so much to physicists, even though it produced nothing you could see or touch. It suggested for the first time a version of exotic matter that isn't exotic at all. Just entanglement, engineered carefully enough to do a job we thought only impossible physics could do. I keep coming back to something a physicist said about this, paraphrased, not quoted directly, that we may have spent 90 years looking for a strange new substance to build a wormhole when the ingredient was sitting inside ordinary quantum mechanics the entire time, waiting for someone to notice. If that's true, it reframes the whole hunt. We weren't missing a material. We were missing a translation. But I don't want to oversell this either, because intellectual honesty matters more to me than a good hook. Even with entanglement doing the heavy lifting, every wormhole anyone has built, in a lab, on a chip, in a simulation, has been microscopic. Smaller than an atom, existing for a fraction of a second before collapsing back into nothing. The gap between that and a tunnel large enough to send a spacecraft through isn't a small technical hurdle. It might be one of the largest gaps in all of physics. Some researchers believe it's not a matter of scale at all, that no amount of engineering will ever bridge it, because the universe simply doesn't allow wormholes bigger than a whisper. Others disagree, and this is where the field gets genuinely divided, not performatively divided the way debates get flattened for headlines, but actually split among serious people who've spent their whole careers on this. Some physicists think macroscopic, stable wormholes are mathematically forbidden, that nature has built in a kind of cosmic safety lock, the same way it seems to prevent time travel paradoxes from ever actually occurring. Stephen Hawking spent years defending a version of this idea. He called it the chronology protection conjecture, the notion that the laws of physics quietly conspire to stop time travel and its stranger cousins, wormholes included, from ever becoming usable, even if the math technically allows them. Nobody has proven he's right. Nobody has proven he's wrong either. And that unresolved tension is exactly where we are right now, this year, with this new paper. Not at an answer, at a fork. One path says wormholes were always a mirage, a beautiful side effect of equations that describe something else entirely, something about time, not tunnels. The other path says we've been asking the wrong question about scale, and that entanglement might eventually unlock something we can't yet imagine engineering. I don't know which one is true. Nobody does, not yet. But I'd rather sit here in the uncertainty with you than pretend the answer's already in. Because here's what I keep thinking about. 90 years ago, a man sat down with the strangest equations of his life and found something folded inside them that even he didn't fully understand. He called it a bridge. We're still trying to figure out what's actually on the other side. There's a moment I keep returning to from that 2026 paper that I haven't told you about yet, and I think it might be the most important part of this whole story. The researchers weren't just redefining what the Einstein-Rosen bridge is. They were asking a much older, much stranger question underneath it. What happens at the very edge of the Big Bang? Stay with me, because this is where the pieces start to click into place. We talk about the Big Bang like it's a single frozen instant, the beginning, full stop, a wall you can't see past. But mathematically, that wall has always been a problem. The equations of general relativity, the same ones Einstein used to find his bridge, break down completely at that point. They don't just get complicated, they stop working. Physicists call it a singularity, a place where the math itself collapses under its own weight, refusing to tell us what actually happened. For decades, that breakdown has been treated as the edge of knowledge, the place where physics throws up its hands and says, past this point, we genuinely do not know. But here's what's quietly radical about connecting this new research to the beginning of everything. If the Einstein-Rosen bridge really is a hinge between two arrows of time rather than a tunnel through space, then a singularity might not be a wall at all. It might be exactly this, a seam, a point where one flow of time folds against another, and instead of the universe simply ending in a knot of impossible density, something on the other side of that fold keeps going, just facing the opposite direction. I want to be careful here, because this is the part where excitement can tip over into something the physics doesn't actually support. This isn't a confirmed theory of what happened at the Big Bang. It's a mathematical resemblance, the same kind of structure showing up in two very different places, which is either a beautiful coincidence or a genuine clue, and right now, honestly, nobody can tell you which. But I don't think it's an accident that this idea makes something in your chest tighten a little when you hear it, because it touches something we don't usually let ourselves think about. What if the beginning wasn't really a beginning? What if it was a fold? A place where something that came before simply changed direction, and what we call the birth of the universe is really just the far side of a hinge none of us can see the other half of. Think about how strange that is to sit with. We've spent generations asking, what came before the Big Bang? And mostly being told the question doesn't even make sense, that time itself started there, so before is meaningless. Maybe that's still true. But this research offers, for the first time in a long while, a mathematically serious way the question could make sense after all. Not a before in the way you and I experienced before. A different arrow, folded against ours at the exact seam where our universe begins. I keep thinking about how personal that feels, even though it shouldn't. Even though this is about space-time and equations and things that have nothing to do with a single human life. But we all carry our own version of this question, don't we? The moment that felt like the end of something. The version of you that existed before the thing that changed everything happened. And the version that exists after it. You don't get to see across that seam either. You only know it's there because everything on this side moves differently than it used to. Maybe that's why the story keeps finding an audience, generation after generation, dressed up in new equations each time. It's not really about wormholes. It's about whether the things that feel like walls, endings, singularities, the edge of what we can know, are actually something softer, a fold instead of a stop. I don't know if that's true, cosmologically. I want to be honest with you about that, because I think you deserve honesty more than you deserve comfort. But I know it's the question the physicists themselves seem to be circling, carefully, in language stripped of any poetry. Because the poetry isn't their job, it's ours, listening from the outside, trying to understand what it might mean if they're right. And there's one more piece of this you need to hear, because it changes how close we might actually be to knowing. Here's the piece I promised you. The reason this might not stay theoretical for much longer, there's a telescope array most people have never heard of, quietly reshaping what we know about the exact region of the sky we've been talking about this whole time, the center of our galaxy. It's called the Event Horizon Telescope, and you might remember it from a few years back when it produced the first ever image of a black hole's shadow. Not Sagittarius A at first. A different one, in a galaxy called ME87, 60 million light-years away. Then in 2022, they turned their focus closer to home and gave us the first real image of Sagittarius A itself. A blurry, glowing ring, orange and gold, wrapped around a darkness so complete it seemed to swallow the concept of darkness itself. That image made headlines everywhere. What didn't make headlines, what almost never does, is what the scientists were actually looking for hidden inside that ring. Not just confirmation that something massive sits there. A signature. A specific pattern in how light bends and how matter behaves at the very edge that would tell them, definitively, whether they were looking at a black hole or something stranger. Because here's something most people don't realize. A wormhole mouth and a black hole from far enough away can look almost identical. Both bend light into a ring. Both swallow anything that crosses too close. The difference isn't in the shadow itself. It's in the details at the edge. How the light behaves in that last sliver of space before it disappears. A black hole's shadow has a particular kind of asymmetry. A particular way the ring flickers and shifts that a wormhole's mouth, mathematically, should not share. We don't have instruments precise enough yet to see that difference clearly, not quite. But the next generation of the array, currently being built and refined, is designed specifically to close that gap. Some of the scientists working on it have said, carefully, off the record more than on it, that within the next decade we may finally have an image sharp enough to answer the question outright. Black hole. Or something else. I want you to sit with how strange that timeline is. Within our lifetimes. Not our grandchildren's. Not some distant future conveniently far enough away that nobody has to be right or wrong about it. Ours. And that changes the shape of this whole story, doesn't it? This isn't really a piece about a mystery that will stay a mystery forever, the way so many big cosmic questions do. This is a piece about a door that might actually open, on a timeline short enough that you and I could be sitting somewhere years from now watching the announcement together. I think that's part of why this topic pulls at people the way it does. Most of the biggest questions in physics feel permanently out of reach. Dark matter. What happened before the Big Bang? Whether other universes exist. We ask them anyway, but there's an unspoken understanding that we're probably not going to get a clean answer in our lifetimes. This one might be different. This one has a deadline. And I think that's worth pausing on because it means the way we're talking about wormholes right now, cautiously, honestly, full of maybe and if and we don't know yet, might not be the way we're talking about them for very much longer. The uncertainty itself has an expiration date. So if you've made it this far with me, thinking about bridges and hinges and folds in time, about a 100-year-old equation that might describe the birth of everything, I want to ask you to do one small thing. Subscribe to this channel and come back for what's next, because we chase exactly these kinds of questions here, every week, the ones sitting right at the edge of what we actually know, waiting for the next piece of evidence to tip them one way or the other. And while you're thinking about all this, I want to know something. If you had to guess, right now, before any telescope gives us the final answer, which way do you lean? Do you think Sagittarius A asterisk is an ordinary black hole, the same as the hundreds of others we've already found? Or is there a small part of you that wants it to be something stranger? Tell me in the comments. I read every single one, and I'm genuinely curious which side of this you fall on. Okay, back to it. Because there's one more thread we haven't pulled yet, and it might be the strangest one of all. It has nothing to do with telescopes or quantum computers or equations from 1935. It has to do with a question physicists almost never let themselves ask out loud, because it sounds too much like something you'd hear in a movie. What if we're not the only ones who've ever asked this question? And what if someone, somewhere, already found the answer? Let's sit with that question, because it's more serious than it sounds. In 2013, the same year, Maldacena connected entanglement to wormholes. A small group of physicists started asking something adjacent to that idea, but stranger. If a sufficiently advanced civilization ever managed to stabilize a wormhole, even a small one, even briefly, would there be any way for us to notice from here? It sounds like the setup to a science fiction plot, but the physics behind the question is completely legitimate, which is exactly why it unsettled people who don't unsettle easily. Here's the reasoning. If exotic matter or its entangled equivalent were used to hold a wormhole mouth open, it would leave a signature. A gravitational fingerprint, subtly different from anything a natural object produces. Natural collapsing stars, natural black holes, they follow predictable patterns. Something engineered to defy gravity's usual behavior would, in theory, stand out. Not obviously, not like a flashing light, but detectably, to instruments sensitive enough and pointed in the right direction, over enough time. A few research groups have quietly proposed searching for exactly this. Not searching for alien radio signals, the way SETI has done for decades, scanning the sky for something intentional, something sent our way on purpose. This is different. This is searching for evidence of engineering, for the accidental fingerprint left behind by something built, not broadcast. Nobody has found anything. I want to be completely clear about that because this is exactly the kind of claim that gets twisted into something it isn't. No credible research group has announced a gravitational anomaly consistent with an artificial wormhole. This isn't a discovery, it's a search criterion, a specific, narrow thing certain scientists now know to look for, in data we're already collecting for other reasons. But here's what I find genuinely striking about it. The mere fact that this search criterion exists, that physicists sat down and worked out, rigorously, what an engineered wormhole would actually look like from light years away, tells you something about how seriously the underlying physics is now being taken. 10 years ago, this conversation would have happened only in the margins, at conferences, over drinks. never in a published paper. Now it's part of the actual toolkit certain observatories quietly keep in mind. I think about Sagittarius A asterisk differently because of this. Not because I believe personally that it's artificial. The evidence overwhelmingly still favors an ordinary, if extreme, black hole. But because the question of how we'd even tell the difference has stopped being philosophical. It's become a checklist, a specific set of measurements, something you could, in principle, run against real data and get a real answer. And maybe that's the quiet thread tying in this entire story together, the one that's been underneath every block so far without me naming it directly. We've spent 90 years treating wormholes as something that lives entirely in imagination and equations, separate from the world we can actually measure. And piece by piece, almost without anyone announcing it, that separation has been dissolving. The math got more rigorous, the instruments got sharper, the search criteria got specific enough to run against real telescopes. None of it has given us a wormhole yet. I don't want to promise you something the evidence doesn't support, but it's given us something almost as strange, if you think about it the right way. It's given us a genuinely testable question about one of the oldest impossible dreams humans have ever had. We used to ask, is a shortcut through the universe even possible? Now we're asking, specifically, precisely, how would we know if one already existed? That's not a small shift. That's the difference between a myth and a hypothesis. And I think that's exactly where we're standing right now. Not at the edge of the myth anymore, at the beginning of the hypothesis. So let's go back to where we started, to that mountain and the two towns on either side of it, wishing for a tunnel straight through. I told you that story like it was simple, a shortcut, a way to skip the long way around. But we've spent this entire hour together learning that the tunnel was never the point. Not really. Einstein wasn't looking for a shortcut when he found his bridge in 1935. He was trying to understand what a particle is. Maldacena wasn't chasing spaceships when he connected entanglement to wormholes. He was trying to understand what gravity and quantum mechanics might have in common. And the physicists who published that paper this year, the ones who quietly reframed a 90-year-old bridge as something closer to a hinge in time. They weren't trying to give us a doorway to the stars either. Every single person in this story went looking for a tunnel and found something about time instead. Maybe that's not a disappointment. Maybe that's the actual discovery. Because think about everything we've touched tonight. A bridge that isn't a bridge. A black hole at the center of our galaxy that might, in some small percentage of possibility, be something else entirely. And a telescope right now sharpening its eye toward exactly that question on a timeline short enough to matter to you. A quantum computer that built a wormhole's mathematics out of nothing but entangled particles, small enough to hold, real enough to measure. A singularity at the beginning of everything that might not be a wall after all, but a fold. One arrow of time meeting another, at a seam neither of us will ever get to stand inside. And underneath all of it, the same quiet question, asked in 100 different disguises. Is the thing that looks like an ending actually an ending? Or is it just the place where something turns around and keeps going, facing a direction we can't see from here? I don't have an answer for you. Nobody does. Not the physicists, not the papers, not the telescopes still being built to look closer. And I think that not knowing is worth protecting, actually, rather than rushing past. Because the moment we get a clean answer, this stops being a question you get to sit inside. It becomes a fact you're simply told. Right now, tonight, it's still yours. You get to wonder about it the same way Einstein did, the same way every person staring up at a night sky full of unreachable stars has wondered about it, for as long as we've had the capacity to look up at all. So here's what I'll leave you with instead of an answer. Somewhere, right now, an instrument built by people who have never met you is quietly gathering light from the exact darkness we've spent this hour discussing. And in some number of years, small enough to matter, that instrument might finally tell us whether the thing at the center of our galaxy is ordinary or extraordinary, whether the bridge Einstein found is a fossil of pure mathematics or a genuine clue about how everything began. You'll know before you'd think. That's the part I can't stop turning over. Not your grandchildren, you. If this found you tonight and it made you feel that particular kind of quiet you feel when a question is bigger than you expected, follow this channel so you're here when the answer starts arriving. And if there's someone in your life who'd sit with a question like this the way you just did, send it to 5 of them. Let them wonder too. Leave a comment and tell me honestly, not performatively, just honestly, what you think is really out there. And if there's a question that's been sitting in the back of your mind, something you've wanted someone to actually take seriously instead of laughing off, tell me that too. That might be exactly what we chase next. Until then, look up. The seam is still out there, somewhere, waiting for the light to reach us.